Okay, guys, we are just getting back after break here. So I'm doing a save as, and we've already got a copy of the post named PST. There is another post file extension that has been allowed ever since about, I want to say X6 or X7. And you'll notice down in the Save As type drop down, the little box down here, we've got PST, which is the post file that you've been used to dealing with. We've got .set, which is a set file which is used to generate a setup sheet using the posting mechanism. There's the PSM file, which is the master post. And then you'll see MC post and MCD post. MC post is the equivalent of a .pst. It's just another file extension. I like MC post because not a lot of other programs use it, and so I can send somebody a .mc post file through email, and most of the time the email program will allow it to go through. It won't try and strip it out the way it does with the PST file extension, because Outlook happens to use PST for their mailboxes. Go figure. MCD post, by the way, the D stands for development. So you can also bin an MCD post, which would give you an MC post and an MCB post, as in the binned portion. So I'm going to save this one as a .mc post. Then I'm going to do a save as, and we're going to call this one simple 5x vector. We're going to do this one as a PST. Now, normally, whenever we have a PST file, we also need to include a PSB file of the same name if it was originally, a part post and then an encrypted portion. What tells MPDLL that there is an encrypted portion that goes along with this post file? Has anybody got a guess? Yep, Zeke's got it. So if I look up here, nothing in the post version line says, hey, there's an encrypted portion. If I scroll all the way down to the very bottom, you'll see we've got the control text. Just above the post text section is where we've got this little start bin locator. The start bin locator tells MPDLL where to stick all the rest of that code, all of the unbinned stuff. So if we just do this, we can remove any association with this PST file to a PSB. Now, there are post blocks and variables and things that are referenced in this PST file that are either created or initialized in the PSB. So if we were to run this post, not only are we missing all of the rotary calculations, but there are other variables that will give us errors. So what I'm going to do, I'm going to get rid of a bunch of stuff. Okay, so we've got our post text. I want to get rid of all this stuff. Okay. So I went and deleted pretty much everything out of this post. We have some constant variable definitions. We have some command variables that have some default settings. And we've got some format statement numbers here. Okay, so I'm going to add in okay, so we're going to start with our $. We're going to output the program number. In order for us to do the program number, we're going to have to format it. So we're going to format it with an O. We're going to use format statement number 4, which is integer, but we actually want 4 leading. So that's format statement number 7. And that's program number. And there's no suffix. So we can do that. So we're going to do our program number. And then we'll do this. We're going to do a string literal. And we're going to force a blank line. So you can force a blank line by putting the asterisk and then $. That'll force a blank line. And now we want to do the first tool change. And what do we need in our tool change? Well, we probably want to output the tool number and then the actual tool change command, MO6. Now, in order for us to get the tool number, we need to format it. So we'll do another FMT. We're going to do it as integer. And we're going to format $, because I know we'll need it. We're going to do D for the tool diameter offset. And we're going to need H for tool length number. So at the tool change, probably want something like this. Okay, we get our safety line, we get our tool change, and now we want our startup position. We can certainly take data from the NCI, and what you'll typically see in a Mastercam or the MP master post is that there are string select tables set up to output strings that are formatted correctly for the machine based on data that is constantly changing in the NCI file. And we use modality to determine when these things are output and when they're not output. So we're going to start out here. Rapid. I'm going to hard code in our work offset. We're going to do XY. We're going to do our tool length number. We're going to get the Z value. Now, in order for us to get output that is formatted, we're going to need to add some format assignments. Okay, so we'll add XYZ for our position there. Now granted, things like rapid mode and the work offset, we can set up logic to grab that from the NCI data itself, just like we would in a generic post. But I just want to show you some sample output of, okay, if we were going to build something from scratch, how do we do the calculations to calculate the rotary positions? So if I take my program here and I post it out, you do Control Alt Shift and the letter P on my keyboard, It's Control Alt Shift P in order to allow me to select a post. And this is my simple 5-axis vector post. And I'm posting out all these operations, and I get some errors. Let's see what my errors are. Only single axis rotation is allowed. Haha, angles may be incorrect. And it's giving me the op ID, 3, 4, 5, blah, blah, blah. And that is because in here, I don't have a setting for rot-ax type. So rot-ax type, I'm going to set it to 9999, or in this case I can use C9K since I already have a variable defined that is that constant value. And in fact, if these were real constants, they would be defined thusly. So it looks like this post at least hasn't been updated in a little while as far as formatting for these go, because these should now be colon equals for constant values. Okay, so we set rot-ax type to 9999, which essentially shuts off the automatic processing. And now we repost, same post processor, and now because we've shut off the warning, this is what we get. Okay, we get our program number, which is probably 0 or 1. It's not set, so it didn't output. So I'm going to force the program number. There's my program number. I get my line like I set up. I get my safety line of code. I get my tool change. I get my Y value. So it looks like X hasn't changed. So it was defaulted to 0, and because it hasn't changed, I only get my Y. And then I get my Z position with Z coming from the NCI file. So we go back in here, and we make sure we force the output. So that way, even if it's 0, we still get the 0 value. So we make that change, we repost, and now we get our position. Okay? If we want to calculate rotary angles, let's see, there isn't a null value in MP, is there? Null value for what? Well, what really happened is that here we set up a format assignment for these variables. When the variables are initialized, if you initialize them with a format assignment, they're automatically set to a value of 0. When a variable is first initialized, MP creates 2 data slots. So when we first create $, MP also creates in the background previous $. When we create Y, MP also creates previous Y, and it does the same thing for all the variables. So Z creates previous Z. So that's why it's important to know, unless you're really trying to access the previous value of a variable, not to ever use PRV in front of it. So we would never initialize a variable starting with PRV underscore, because this is what would happen. If I say I wanted to create my own variable, because it's not predefined, I can't use $sign at the end. So if I created PRV my x, this would be a terrible name for a variable, because what would happen is we would get this. PRV my x would be the current, and there would be a previous PRV my x. So it always takes PRV underscore and adds it to the front. So you wouldn't want to do that. And so in this case, for example, program number creates in the background previous program number. And when we initialize a value, we automatically set both the current and the previous, in the case of a format assignment, to 0. So because the current value of program number is 0 and the previous value of program number is 0, modality means that when we read this here, it doesn't output unless we force it. And the same thing is what happened here with our x. Because the current value is 0, and when we initialized x $sign, the previous value got set to 0. The current value is 0, so by default it doesn't output. Now, one of the things that we could have done, we could have also gotten around this problem by doing this. I'm going to take off the asterisk values, the force characters. We're going to repost and look at it 1 second. So let's look again. Okay, so we get no x, we get no program number. Another way to accomplish the same thing would be to do this. I'm initializing the values so that if it happens to be a 0 value, it will still output, because now the previous value is going to be set to -1. So we'll set x $sign, and we can initialize it to -1, or sometimes we'll do something like this. We'll initialize it to like -9999, because there's almost no way that the current value is going to be -9999. So we'll do this for y, and we'll do it for z. Because what's going to happen now is modality is going to take over, and the previous values of these variables are all going to be 9999 negative, and the current value is going to be 0, which means that here and here we will get output. So we've initialized all the previous values, and now we get our x and we get our program number like we expect to. Okay, so rotary calculations. In this Volume 2 reference guide, there is a section in here that talks about deriving angles using the vector math. Okay, this is all 4-axis rotation, axis sub, Okay. Processing 5-axis motion. The following examples illustrate a very simple 5-axis post. The basic routines can support the table-on-table type machines, table and head tilt, or head-head, gantry style machines. For this example, assume X abs, Y abs, and Z abs are user-defined variables for the linear output. C and A are predefined variables that are used for the uncontrolled rotary output. U abs, V abs, W abs, Vec X, Vec Y, and Vec Z are user-defined variables for intermediate calculations. Okay, yeah, and it talks about even though the Rodax type settings 2 and 4 enable some routines for table-table and head-head machine configurations, their implementation can be very confusing because of the various post blocks called for different rotary types. Here is a simple approach where Rodax type is set to a value greater than 6. Assume this initialization. Rodax type 9999. This simplifies post block calls because all calls for output post blocks will go through the predefined post block PMX0 first. The post customization file can handle all calculations at one location. So we're going to set up some vectors here, some variables. So let's do this. Okay, so we'll set up X, Y, and Z. Okay, so we got Vec X, Vec Y, and Vec Z. I'm going to do U abs, V abs, and W abs. Okay. To eliminate other possible problems with drill cycles and arc motion, they are all converted to linear. So again, this is just a very simple example. We're going to set lin arc to yes, which basically says linearize all arcs. And we're going to do use canned. Can't drill, can't miss one, can't miss two. Drill, miss one, miss two, use can pack, use can pap, 1, 2, 3, 4, 5, 6, 7, 8. So basically what we're doing here is we're taking all of the arc data and we're converting it into linear, and we're taking all of the drill cycles and we're converting them into the positions themselves. We're going to use the modern style of drilling, where rapid type V7 setting is 0, and the tool change after technique to permit calculating the rotary position with the tool change. So we want rapid type V7 set to 0, and tool change aft set to 2. Okay, so we're not doing polar or axis sub. Now we're looking at how do we process this 5-axis data. 4 or 5-axis vectors, basically. So Mastercam 3-axis toolpaths, which are tool plane based, and 5-axis toolpaths, which are vector based, conflict in the data presented to the post executable. The 3-axis toolpath coordinates are relative to the tool plane view. They don't match the WCS view. The 5-axis toolpath vectors are relative to the tool plane view, but each vector must be calculated to get its direction relative to the machine base view. It is much easier to process all of this data if it is presented in a consistent manner. I think this here is really just a cover to say we're not going to show you how to do everything. We're going to show you a quick, simple example to explain the mathematics, and if the vector and matrix math is not your strong suit, buy a post from our reseller. I think that's what that's what they're saying without saying it, if you will, because they certainly do a good job of doing this inside their generic post. And what they're saying is that instead of showing you an example that does all these things, this can be accomplished by mapping all the data to a common machine-based matrix. The matrix is predefined. So define a machine-based matrix relative to the WCS, draw geometry and create toolpaths relative to this matrix. Always assume the centers of the rotation axes converge at the WCS origin, and that the machine work coordinate 0 position is set at this location. If table machines with tool plane positioning, so it says table machines with tool plane positioning can have the work coordinate 0 position at other locations. So here's the definition of the machine-based matrix. It matches the top view. So MATB 1 through MATB 9 is predefined in the post, or they're predefined MP variables. So we'll go down, actually we'll do this near the top here. So we're doing MATB 1 through MATB 9. And we need to initialize it. To either a 0 or a 1. For the top view, 1, 0, 0, 0, 1, 0, 0, 0, 1. So the first three describe the X, the next three describe the Y, and the last three describe the Z. We need another matrix. So it says you must create 2 user-defined matrices, one for the mapping matrix and one for a reference to represent the WCS matrix. So let's get our shift. Okay, and this is TMTX1. Okay, so we've got our matrix here. 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. Now, I realize I named these slightly different. So you'll notice I've got TM, TX, 1, 2, and 3, TM, TY, 1, 2, and 3, and TMTZ 1, 2, and 3. What matters is that I have 9 variables in order. When we use vector and matrix math functions, we always specify the first variable in the list of variables. And MP always assumes that we're working with either 3 variables in a list or 9 variables in a list. So it's important for us not to interrupt the order. Okay, so we've got that matrix there. Yeah, I mean, you just want to keep it, you want to keep them in the defined order that you use them, and you want to make sure that the names are unique and that they make sense to you for what you're doing. So we're going to do the result matrix here. Result matrix multiply. Okay, so this one is the result matrix. RMTX1 and I can leave these RMTX1, X2, X3, Y1, Y2, Y3 if I want to. It doesn't matter if I do this, as long as each of these variable names is unique. That's why I have to do increment the numbers here 1 through 9 if the rest of the name is the same. Here, I can get away with having 1, 2, 3, 1, 2, 3, 1, 2, 3 because I'm changing X to Y to Z. I like naming them this way because it reminds me that this is all part of the X vector, this is all part of the Y vector, and this is all part of the z vector. In other words, this is the x component of my z, this is the y component of my z, and this is the z component of my z vector. You can also do the same thing by doing this without the numbers. Okay, so this is x, 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 y, x, z. This is y, x, y, y, my y, the z component of my y. So this is the x component of my z, this is the y component of my z, and this is the z component of my z. Okay, so there's my result matrix, and then I want my vector constants. Okay, so I need you can see here a axis x, okay, so we've got a axis x, a axis y, a axis z. We've got b axis x, y, and z, 0, 0, 1. And we've got c axis x, y, and z. So this is a matrix, but these were created with as basically three independent vector definitions. Here's a vector that points straight up along z. Here's a vector that points positive y. Here's a vector that points positive x. Okay. When the post is run, when the post is run, you must create a mapping matrix at each tool change. The predefined post block, P tool change 1002, is called prior to the output tool change and the call to PMX0, which is where you can set the mapping matrix with the code shown here. So at P tool change 1002, we take TMTX1, we do matrix transpose with MATB1. Then we multiply a matrix, MMUL, matrix multiply. And you'll notice we multiply TMTX1. Here, let me blow this up a little bit. We multiply TMTX1 with M1, which is the tool plane matrix. You'll see the result matrix, multiply. So this code puts the tool plane matrix into the matrix starting with TMTX1, first in terms of the machine base, then in terms of the WCS. It puts the result in terms of the machine base matrix. This creates a matrix that can be used to map positions into the machine base matrix. All the NCI position data can then be placed in terms of the machine-based matrix with this code. Use the predefined post block PMX0 because it is called prior to the NC output calls with rotax type set above 6. This includes calls from the motion breakup procedures. So then we use this code down here to map our coordinates. So first we're going to put this stuff in, then we're going to see how it runs. So we need our P tool change 1002. Okay, and this is called before all tool change events. So we're going to do the matrix transpose. We're going to transpose MATB1. Basically, we're copying MATB1 into TMTX1. We already initialized it, so technically we don't need to do that step, but this will make sure that it's always set to equal our machine-based matrix. So TMTX1 equals matrix multiply, or multiplying TMTX1 by M1 $. So this is where we multiply this matrix by the tool plane matrix. And this is weird because what we're doing is we're multiplying 9 variables by 9 other variables. This function is a matrix function, and a matrix function always uses 9 variables. The problem is we can only pass one name as the argument for each of these arguments. So we have to use the name that begins the ordered list of variables. So now we do RMTX1 equals MATT M1. RMTX1 equals matrix multiply, and it is RMTX1 by A axis X. It's funny that we're using A axis X there. Okay, and then it says to multiply it by MATB1. So if I go and look at check something real quick, guys. Same thing. Okay. All right. So in addition, PMX0 is used to map the coordinates. So XABS equals VMAP, which maps the vector defined relative to top view to matrix M, returns the map vector. So XABS equals VMAP X $ into RMTX1. And then we say if it's not 5-axis, so if not mil5, UABS equals vector addition XABS TMT. Ooh. And it says X7. But it depends on how we named our variables. So if we go back up to TMT, so TMT X7, I named TMT Z1. So that's the difference in the naming convention. So I got to be a little bit careful with that in the example. So that's TMT Z1. Else, UABS equals VMAP U $, and we're going to map it into RMTX1. So we're going to make the direction vector vecx equals v sub uabs and xabs. So we're going to subtract the two. Then we're going to normalize the vector. In other words, set its length equal to 1 unit. This MP language code first maps the X, Y, and Z positions to the machine base. Next, it creates the U, V, and W positions for the 3-axis toolpath by adding the Z component of the mapped tool plane matrix to the X, Y, and Z positions. For 5-axis paths, it maps the U, V, W positions to the machine base and recalculates the tool vector. The final result is that all the data, regardless of toolpath type or original matrix, is expressed in terms of the machine base with a tool direction vector. After mapping, the post must resolve the angles and rotate positions based on the machine type: table-table, table-head, or head-head. The following sections contain basic information on performing these calculations. Note, setting up the calculations for a particular machine requires studying the axis motion, determining the logical rotary zero positions, etc. These tasks are not trivial, and you may need the assistance of your Mastercam dealer in developing or modifying post-customization files to meet your needs. for the following example, assume the data is x abs, y abs, and z abs of 1, 1, 1, and vec x, vec y, and vec z of 0.5773, 503, blah, 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 blah. Okay, each post line is examined to demonstrate the vector math used. This example uses a head-head machine, similar to the following. So this is showing us the head-head with the specified machine dynamics in terms of the machine base. So you can see we've got B rotating on Y, and we've got C rotating on the Z. And here is the code they give us for completing the calculations for the rotary axis. Okay, so this is for the head-head style. And then they explain it. This code down here supports table-table, table-head, or head-head machine configurations. To address a table rotation, also rotate the position with the vector. Here is the modified code that behaves as a table-table machine. Did they start with C over here? Yeah, they did. And C and A. So, this is what we'll add in here. Okay, so in PMX0, we've mapped the vectors. So we do C $ equals A tan 2. And A tan 2 is the secret to making all of this stuff work. Because A tan 2 is the function that calculates the angle between two vectors. The angle is a positive angle between 0 and 360 measured from X to Y. So now we're going to do A tan 2, and we're going to say minus vec Y rotating towards minus vec X. Then axis X. So axis X is a math helper variable, rotation vector used with the rotate functions ROTP and ROTV. So axis X equals vector equate C-axis X. So what we're doing here is we're setting this rotation vector, this helper vector, to the C-axis. Because this is the vector that starts with C-axis X. Getting triggy with it. Yeah, I like that. That's awesome. Yeah, so C-axis X. So we're setting the rotation vector to be vertical. So vec X equals rotate vector minus C $, and we're rotating it by vec X. So let's put in our little comments here. So this is calculate C angle. Okay, we define the rotation vector for ROTV. We're going to rotate vec x into xz. You do ROTV minus c. X abs. Okay, we're going to rotate x abs into xz. A dollar sign equals A tan 2 rotating minus vec x to vec z. Calculate the A angle. Axis x equals vector equate B axis x we're going to redefine the rotation vector. Then we're going to rotate x abs to be vertical. I think it has to do with the way that it was originally defined. If we go back and look at you can see that it's negative here. When we calculate the rotation direction. It may need to be negative, actually. So what we'd want to do here make sure we format these. Okay, make sure we put that on there. Jeremy asks if this information is in the newest MP doc. It is, but it's hidden. So if I pull up the latest MP documentation, you go through all of these documents, it's not in there. It's in legacy docs. So if you go into legacy docs, you'll see MP ref legacy, and it is in rotary processing. So it is there. Starting let's get through this. Processing 5-axis motion. Yeah, they haven't updated it to the newest format stuff. Because again, this is about writing your own logic to process the 5-axis. They do need to update it. Yeah, it probably hasn't changed much. I know they're going to be putting in a new section that deals with, okay, we've updated our generic Fanuc 5x post to read the machine definition, so now you can go and change your little, rotary rotation axis in the WCS and the 0 position. But if you still want to write your own logic, you still can. So we've updated X, Y, and Z abs. And what we're going to do now is do the same thing, but we're going to change this. P tool change 0. We're also going to do this at P tool change. This is P tool change 0. And let's do this. I think it is. We'll do the feed rate. Okay. We've already set lin arc, so we're going to linearize any arc data that we find. So let's do that. And it's got A and C at the tool change. So now we repost. Okay, so got our positioning. Now we do our tool change. We change to tool 19. You can see we're getting our angle output. So here we started at A90, C270. Now keep in mind, this may not necessarily be correct for this machine. It's correct for how we configured it. But at the first tool change, we get A90, C270, and in our linear, we're not changing our A and C. So we would have to do this. Rapid X abs and then A $, C $. And for linear output, A and C, and we save it. Repost. And you can see C rotating, so we start at C270. Now we're rotating up. Cross over the 0. And rotate up to 270, hit 270, and we back out. Now we go to the tool change. Okay, and all we do is we rotate C180. And this guy is a drill op. We don't have anything to handle the drill op. So then we go to the next tool change. We go to 270. We actually do some work here. Looks like that's funky. And we tool change and we go to C90 and we do something. And we tool change and we go to 180. Okay? And we tool change and we go back to C0. Now you'll notice, yeah, could we run this code? Probably. I mean, we obviously have some things that it didn't like. Okay, X and Y defaulting to C9K, that's not going to work, obviously. And keep in mind, we're also taking all of our arc output and we're linearizing it. So could we run this code? Maybe. There's probably still some things that we got to tweak to it, obviously. In this documentation, it also tells us this very simple example does not address feed rate calculations, rotary axis windup, rotary limits, offsetting the axes. All these things must be coded with the MP language into the post customization file. Okay, so there's still quite a bit left to do. This is about as basic an example as you can get. And believe me, when we say basic and you start looking at code like this, it is anything but basic, right? It's complex. But this is the code that we need to take a vector, rotate it into the plane, and then use ATAN2 to calculate the rotary axis angle. Yes, there's still a ton of stuff left, that we could do to this. And there are some things that we can check out because we may not have our settings here in PMX0 correct for the rotation we're trying to do. And if that's true, then we can change these guys. You know, we may have to change the vector that we're rotating about. But once we do that, we should be able to get output that is correct for any type of machine. And we can do it without needing any type of PSB file if we know how to perform the math. Okay, all of the math functionality already exists for us and has for, 100 years, I don't know, 70 years, something like that, 80 years. I mean, vector math has been around for a long time. Linear algebra has been around. They were doing stuff like this in the 1930s. It's just their equipment sucked and they didn't have computers. So you had to do everything by hand and it was tedious and crazy. So, all right. We are running a little bit over on time. I know that me typing out, what is this? 20 lines of code makes stuff work, but it doesn't exactly explain in very great detail, right? So, I can send you a copy of this stuff, honestly, but what I did, literally, character for character, it's all right here for you. I literally just typed in the code that was in P tool change 1002. Okay, I typed this out verbatim. I typed this out verbatim. And then I typed this out verbatim, minus a few variable changes, which are no big deal. So it's like, I could send you that, but honestly, I'd rather have you type it out. Get comfortable with reading through here and typing it in there. The only things that I changed really is some of these variables. Axis X, $C$, $A$. The only thing that's really different is that some of these guys are predefined. But you'll see that when you start typing it in here. Okay? So, my inclination is to have you guys type it out on your own. Try to make this work on your own. And give it a try. If you get stuck, I'll be happy to send you my example. How's that? I want you to try it first. Because, I can give it to you, but it's already given to you. It's already given to you here. Okay? Good. It's already given to you here. I want you to try it on your own. Try typing it out. See if you can make it work. And then you'll find something. You'll get an error somewhere. And the error will tell you something. And it'll give you a direction to start go chasing down. So try it on your own. If you really get stuck, let me know. I'll be happy to send you a copy of it. And you can compare, what I did to what you did. Yeah, that's just it. Zeke makes a good point. The basics will never go away, right? The math that underpins all of these calculations hasn't changed in 30 years. Hasn't changed in, since the creation of time. If you want to come down to it, somebody had to figure it out. But once they figured it out, the math still works as well as it did when the guy who first figured it out. The math still works. And that's the beauty of it, right? SOHCAHTOA, baby. You got it. So give it a try. Read through here. Then go and have a drink and let your mind unwind, and then read through it again, and then read through it again. I don't think it was until probably, the 10th time through it that I really started to catch on to what they were doing. But this section has been around since version 9. So all of this example code has been there for over 20 years. Probably going on 30 now at this point. No, the example I should say is at least 20 years old, because it was probably 2001, 2002, so I guess 15 years. But, these math functions have been in the post for a long, long time. ATAN 2, man. That's where it all comes from. Okay? So, there may be questions. Let's wait till tomorrow for those questions. Okay? We're going to do Wednesday office hours. Same bat time, same bat channel. Okay? And we'll do 2 hours. So we're going to do 7:30 to 9:30. We'll do like our standard, 10, 15-minute break in the middle. But yeah, tomorrow. So we're going to do an office hours on Wednesday tomorrow. And we're going to do a normal one on Saturday as well, considering it's our last one. Okay, so if you can't make it tomorrow, don't worry. We will still be doing our regular Saturday session as well. Right? So 7:30, same bat time, same bat channel. Find the center of rotation without being able to send the machine to A90. Yeah. Yeah, tooling ball. You've got 90 and some math. Thursday. Well, we are having normal class on Thursday. We are also having office hours tomorrow. So, yeah, you have at least 90 degrees of total rotation, right? You got like one of those plus, okay. So if you've got that, if you've got that, you can start at 0. You can find the center of your tooling ball. You can rotate minus 90. And by touching off on that tooling ball, you can find out what the offset is. Yeah. You need a tool with a known length and a known diameter. And we can go from there. So yeah, as long as you've got 90 degrees of rotation, you can touch off on that tooling ball with a known tool. You can rotate 90. You can touch off the tooling ball with a known tool. And there is a procedure for being able to find what that offset is. We just have to come up with it. Yeah. So Jeremy's hitting this important